coordination compounds. We are going to start with this lesson, coordination compounds. In the previous lesson we had learnt that transition elements, they can form coordination compounds or complex compounds. So we are going to study about coordination compounds in which the metal ion is a transition element. Now we have also studied about we know certain complex compounds which we come across in our day-to-day lives. One is hemoglobin. In hemoglobin, the central metal ion is iron. Now chlorophyll also is a complex compound, but in chlorophyll the central metal ion is not a transition element, it is magnesium. Then in vitamin B12 complex, central metal ion is cobalt, which is all this complex is vitamin B12 complex is also a complex. It is a coordination compound. From time to time, different theories have been given to explain the coordination compounds, the complex compounds, their nature, their geometry, etc. Werner gave the first theory, and in his theory he introduced the concept of primary valency and the secondary valency. Now primary valencies are the oxidation number of the central metal ion, whereas the secondary valencies are the number of groups which are present around the central metal ion, that is the coordination number. Primary valency is the oxidation number and the secondary valency is the coordination number of the central metal ion. So on this basis he described the geometry of the complex, etc. But this theory was it had certain shortcomings, there were certain flaws, so it was not accepted much. Now there is a difference between a double salt and a complex salt. Difference between a double salt, example of a double salt is Mohr salt or potash alum, Fitkari. Now a double salt, you can take the example of a double salt which is potash alum or Mohr salt. Mohr salt is what? Ferrous sulfate, ammonium sulfate, twice SO4 and 6H2O. Now when this ionizes, it will form ferrous ions, sulfate ions plus ammonium ions plus of course water. So all the ions which are present in the salt will go into the solution, and you can test for ferrous ion, you can test for sulfate ions or ammonium ions, all will give a positive test, that is the ions are free. But what about the complex salt? You can take the example of a complex salt like K4FeCN6. K4FeCN6. Now this entity which is present within the square bracket is the complex ion. Now when this ionizes, it will form 4K plus FeCN6 minus 4. Now if you test for potassium ions, you will get a positive test, but if you test for ferrous ions or cyanide ions, you will not get any test, because these ions are present in the complex, within the complex, they are forming a complex, they are not free, so they will not give any test. So this is the difference between a complex salt and a double salt. I hope I am clear. Now moving ahead. Now what are complex compounds? What is how will you explain the formation of a complex compound? Now, in a complex compound, you have a transition element which is present in the center. You have, suppose M is the transition element. Suppose M is the transition element. This is present in the center, and around M are present different groups, or they may be anions or neutral molecules which are coordinating towards the central metal ion. These groups which are coordinating means they are giving their lone pair of electrons. If they are neutral molecules, they are coordinating through their lone pair of electrons. If they are anions, they are giving the electron pairs to the central metal ion. So these groups are known as ligands. They are known as ligands, and they are coordinating. They are giving their lone pair of electron to the central metal ion, and we place this whole metal along with the ligand in one square bracket. This is the coordination entity. The whole entity which is present in the square bracket is the coordination entity. Now, central metal ion should possess vacant d orbitals to accommodate the electrons which are being given by the ligands. Central metal ion should have vacant d orbitals which are being vacant d orbitals in which the electrons have to be accommodated. Electron pairs which are coming from the ligands, they have to be accommodated. So d orbitals, the transition elements have vacant d orbitals, so these electron pairs can be accommodated here. Now, what are ligands? Ligands are groups. They may be anions, they can be neutral molecules which are donating the electron pairs to the metal ion. Now, these ligands, we can describe them. These ligands may have only one coordinating site. We call them as monodentate ligand. We call them as monodentate ligand or unidentate ligand. Monodentate or unidentate ligand. It means there is only one atom in the group which is coordinating. We call it as monodentate ligand. There can be a bidentate ligand also. Bidentate means there are two coordinating sites present in the ligand. For example, oxalate anion. Oxalate anion has two minus charges. So it can coordinate with the central metal ion like this. See. So you can see, because of a bidentate ligand, there is a ring formation. Here you can see there is a ring formation taking place. Due to the bidentate ligand, there is a ring formation here, and because of this ring formation, this ring formation is known as chelation. It is known as chelation. This ring formation is known as chelation, and these rings are chelate rings. Now, this is when there are two or more than two atoms which can be coordinated to the central metal ion from the ligand, then only ring formation is possible. Now, there may be groups, there may be ligands which may have more than two we have discussed, but there can be more than two coordinating sites. Then they are known as polydentate ligands. Such ligands are known as polydentate ligands. Now, there is a very good example of a polydentate ligand. ethylene diamine tetraacetate anion. This is an example of a hexadentate ligand. Hexadentate ligand means there are 6 coordinating sites. You can see this is ethylene diamine. Ethylene diamine is CH2 and NH2. Okay, CH2 and NH2. So you can see there are 2 nitrogen atoms each having lone pair of electrons. Nitrogen has lone pair of electron which can be coordinated. Then if the 2 hydrogen atoms are removed and in place of these 2 hydrogen atoms you have what? CH2 CHO group. If you have CH2 COO minus group, CH2COO minus, CH2COO minus. Similarly here also, if you have 2 acetate radicals present here also, CH2COO minus, then there will be 6 coordinating sites present, as you can see here. Electrons can be donated through acetate ions 1, 2, 3, 4 and 2 from nitrogen also. So at 6 positions, from 6 positions electrons can be donated to the central metal ion. So such a ligand here you can say is a hexadentate ligand. So now we can describe what is denticity of a ligand. What is denticity of a ligand? Denticity. What is denticity of a ligand? Now, denticity of a ligand is the number of such groups which are being coordinated to the central metal ion. On this basis, we had described a unidentate or a monodentate ligand, bidentate ligand, polydentate ligand. Then there can be ambidentate ligands also. Ambidentate ligands. Now in ambidentate ligands, there in the same ligand there can be 2 atoms which can coordinate. Now for example here you can see this is thiocyanate SCN. Now electron pair is being donated through sulfur atom to the metal atom. Sulfur to metal. Coordination is through sulfur. But in isothiocyanate, coordination is not through sulfur, it is through nitrogen atom. The ligand is the same, but coordination is through nitrogen atom. So this is isothiocyanate and this is thiocyanate. Similarly here nitrito N, that is through nitrogen, coordination is possible, and here nitrito O, through the oxygen here, coordination is possible. So such ligands are known as ambidentate ligand. Ambidentate ligand. Such ligands are known as ambidentate ligands. Then what is coordination number? Coordination number is the number of groups which are present around the metal ion. For example, if you have Cu NH3 whole 4 plus 2, then the coordination number is 4, because there are 4 ammonia groups, 4 ammonia molecules which are coordinating from the 4 sides. So coordination number is 4. So the number of groups which are present around the central metal ion is the coordination number. Now we proceed to the next point, which is the oxidation number of central metal ion. Now oxidation number of the metal ion has to be calculated. oxidation number. If suppose you have again CuNH3 whole 4 plus 2 plus 2. Now what is the oxidation number of copper? We have to find out. The ligand present here is ammonia, and ammonia is a neutral ligand. So the contribution from ammonia will be 0. So we can calculate, if for copper we put x here, x plus 0 into 4, because there are 4 ammonia molecules, is equal to plus 2. X will be equal to how much? Plus 2. So oxidation number of copper is 2. Similarly, in FeCN6, FeCN6 minus 4, ferricyanide. What is the oxidation state of Fe? Put X here. X plus, there are 6 cyanide ions and the charge is -1. So -1 into 6 is -6. So X minus 6 equals how much? Equals -4. So X is equal to plus 6 minus 4, X equals 2. So oxidation number of Fe is 2. This is how we calculate the oxidation number of Fe. Next we will discuss about the nomenclature in our next video. Thank you.